So I do want to be conscious of time and give a brief overview of what SATNOGS is and what we're trying to accomplish. I will be here all day today and all day tomorrow wearing a SATNOGS shirt, so if there are a lot of questions or you're interested and I didn't give you enough in this presentation, either check out the paper in the booklet or come find me. It's a weird name that stands for Satellite Network Open Ground Stations, so we call it SATNOGS. And to understand what we're trying to accomplish here, we want to look at the problem of just the massive growth of CubeSats in space today. There are tons of satellites being launched. They're getting cheaper, more frequently launched, and a lot of these have research payloads on them, and the data that's coming down from these satellites is picked up maybe by a university once or twice a day, and beyond that they are indebted to amateur radio operators or satellite enthusiasts to actually get them more data than what they can get from their own ground station. And there are a lot of people that do this. You know, talk about leaderboards, there's a big community and a lot of competition around satellite enthusiasts who produce this data for the researchers that are looking for it. But this is a manual process. Somebody has to be sitting at a computer, they have to be running the rotator, they have to be running the SDR, they have to be tuning the Doppler, everything, all of this stuff, and then that's even before you get to the demodulating and then the decoding of the actual data and then the uploading of the data. It's a manual process. Someone might do this over a weekend or do this after work as they're sitting at their computer. And that does not scale. If you look at this graph here, shows the number of CubeSats that have been launched, and going up to this year here, the blue is yet to be launched for 2017, and then future launches that are currently planned. A group of volunteers that are just doing this on their own time, sitting at a computer, can't do this and can't keep up with this. So our goal is to automate the process, make it fully automated from beginning to end, and that way we can automate the satellite tracking, automate the RF collection, automate the uploading of it, and automate dashboards as well. In addition to that, we have a secondary goal of making this cheaper to accomplish. A good ground station today is going to set you back, quite a couple thousands of dollars. With some decent antennas and a decent rotator, commercial rotator. So there are a couple of goals of SATNOGS, one of which is to write the software that's going to automate this. The other is hardware. Now the software is modular. It works with any kind of rotator that's out there that's supported by HamLib software today, which is most commercial rotators. And we also have a design that you can 3D print your own rotator. And that sounds pretty crazy, but I can attest to this design actually surviving 4 seasons in Indiana. And it works. Now, you're not going to put a pair of M² heavy antennas on something like this, but the antennas that I used were also of homebrew design, PVC piping, 3D printed element holders, and what have you. So it was a very lightweight antenna and a very lightweight design. And so about $300 fully assembled. That 80/20 extrusion and hardware really packs the punch. So beyond that, let's say you already have a rotator or you've built a rotator, then everything else that's involved is referenced to a Raspberry Pi 3 and an RTL SDR dongle. That's it. That's all you need to get into SATNOGS today. And that's what you need to take an existing ground station and put it on our network today. It does work with other SDR devices. Anything that's supported by GNU Radio Osmo SDR is technically supported by SATNOGS, but some of them are not going to be able to be handled by the Raspberry Pi, so we just suggest a $25 RTL SDR. It works perfectly. So let's get into the web components. Oh, I'm so sorry. I converted this from Google Docs, and some of it fell off the screen. We have a couple of websites and web components that are critical to making this entire ecosystem work. The first is our database, db.satnogs.org. This is a crowdsourced, open database of satellites and satellite details. Everything from the TLEs that are collected from Celestrac, to transmitter data of the satellites. All of this is kept in a single database. And this database also has an API that's openly accessible to all. So, for example, we had somebody work with gpredict, which is a Linux-based tracking, rotator, and frequency changing application. And it can actually pull down the latest frequencies and data from our database. As well as keeping all of the data about the satellites, we keep data that's collected for the satellites in this database as well. So all of the frames that we collect are stored in this database. And there are also third-party applications that are out there today that, like the DK3WN telemetry forwarder for Windows, that will forward packets automatically to our database. And that's, again, another leaderboard opportunity where we have some that are really striving for the top. And that, again, that website's openly accessible to all. You can go in there, you can sign up for an account and actually download the frames that are uploaded for any satellite that we have frames for today. Then let's go to network. Network.satnogs.org is the brain behind SATNOGS. It's the central scheduling system where all of these clients and these ground stations are out there. They all check into the network, and the network is where we schedule observations to be made. The network is where we handle and avoid potential conflicts in scheduling. A good example is, let's say I go to the website network.satnogs.org, and I want to collect all telemetry for UPSAT from 8 o'clock to 1400. It'll schedule every ground station that's available on the network during that time period to collect data. It'll give them the TLE, it'll give them the time to collect, it'll give them the frequency that we're targeting, and it will give them the mode that we're targeting. That way we have different ways of handling different modes in the client. A good example of this was this morning with QuickCom. I think QuickCom is the name of QuickCom 1 was just released from ISS this morning, I think. So we had observers who were scheduling that as quickly as they could to try and catch the first beacons from the satellites around the world. And then it collects observations when they're finished. We collect the waterfalls, we collect the demodulated audio, and then we collect any decoded data that the client was able to capture. This is what our development network looks like. Our production network is a lot more sparse than this today, but this is indicative of a lot of people who are building their own ground stations. They might be doing the 3D printed design, and they've put a pin on our network, or they might be doing even a standalone design with fixed antennas. We do support anything we can get a signal from. So definitely Yagis with a rotator is going to work the best, but sometimes that's not always possible. And so fixed antennas like turnstiles and Lindenblads have been really successful on our network as well. Burns has gotten quite a few observations on our network with his Lindenblad antennas. So that takes us to the client. Let's say you've got this Raspberry Pi 3 sitting at home and you've got an RTL SDR. What does this thing do? It checks in with the network website once a minute. It says, hey, do you have any jobs for me? Do you have any jobs? Do you have any jobs? As soon as there is a job, it waits for the time for that observation to begin, and then it'll control the rotator, and it'll track the satellite as it's passing over if there is a rotator. If there's not a rotator, then there's nothing to be done there. And it'll kick off a GUNI radio script. Depending on the mode that it's given for the satellite, there might be a different script. We're going to handle CW differently than FM, for example. And then it'll also adjust the frequency for Doppler shift so that we're constantly on target for that satellite. It generates a waterfall. It generates audio that's demodulated from that script. And once that's all done, uploads the results back to the network. In the case where we have support for actually decoding the data, it'll upload the decoded data as well. That's kind of where we've made some progress and we've got some ways to go. And today it comes, we've made a lot of progress and the client comes in a ready-to-flash Raspberry Pi image. That's been the biggest step that we've made in the Raspberry, on the client side, is getting that image and a SATNOGS setup command, which makes it easy to configure the SATNOGS client on a Raspberry Pi. It makes it easy to update it, get new software on there and what have you. On the network support side, we've recently added support for APT imagery from NOAA satellites and FSK 9600 baud frames. And we're working on more modes as well as we speak. On the database side, we standardized on the SIDS frame, the SIDS protocol for handling frames so that we can automatically take packets from other applications that are supporting this. And what's coming up next? So uploading of more captured frames to the database from the network. Right now we have a little bit of split brain between the database and the network. We're collecting frames in the database, and we're also collecting frames in the network, and we need to get them from the network to the database. Also up is automated observation scheduling. Right now, my ground station at home is probably doing 30 to 50 observations in a 24-hour period. I'm not touching it. I'm not doing anything. There are a couple of enthusiasts in Greece who are keeping my ground station very busy. And that only goes so far. Again, the next question is, okay, they can only do so much scheduling. What about the blanks? How can we fill in the blanks? What can we capture when we're not consciously observing something? And so that's going to be coming up. And on the client, we're going to be decoding more modes. CW decoder coming soon, 1200 baud FSK, VPSK modes. Anything we can get the expertise on the GNU radio side to program in and get the help to program in, we're going to write support for. And my favorite, and what I'm looking forward to the most, is telemetry dashboards. A mock-up image here we've got. So we have over 8 million frames in the database today across the dozens of different satellites. And now we need to be able to visualize that data. So having a dashboard available for every satellite that we have data for is the ultimate goal. So if you're interested, how to get involved. So we're always looking for more ground stations, of course. If you have a ground station at home and you're using it on the weekends, we would love to use it on the weekdays. All it takes is a Raspberry Pi 3 and an RTL SDR to get going. And our documentations are up on wiki.satnogs.org to get you going there. Programming-wise, this is an open source application. All of the sources up on GitHub, everything from the websites to the client itself is all open source. It's all a community built project that's sponsored by the Libre Space Foundation, which is main goal is to keep space free and to make sure all of this data is free in the end as well. So programmers are always needed. I got a couple minutes. If our network is working here, I can go in and maybe show. Maybe. Okay, this will be an APT image that was captured from a NOAA satellite. And this actually came from Burns' house. So his station, again, this was somebody in Greece who scheduled this observation, wanted to see what the NOAA imagery was going to look like. You've got the waterfall here that was generated by the client. You can kind of see the APT there, and got the data as well that came down as an automatically generated file. This took nobody at the keyboard to do anything other than click a button on this website that said, I want this imagery during this time over this location. Another time, let's see. We can do FM audio as well. This is an SO50 pass. You can see it in the waterfall there, pretty strong.
What's your house?
That is nice. This one would be off of a 5500 with a couple of M-squared antennas on them, so it works pretty nice. But the conference is a little slow here.
What format is the audio story?
It's actually OGG compressed. So we don't handle raw audio data just because of the bandwidth challenges and the storage challenges on the network side that would come with. We are talking about making that an option, and it is an option in the client. If you wanted to save it locally and have the raw data locally, it would be on the Raspberry Pi. But we have a built-in player here. Oh, but there's no audio. You would hear the FM contact through SO50 at this point. Also, you could download the audio right here, which is handy in data modes. I'll load this one up. This was FSK. And if I wanted to process that with another application, all I need to do is click this button and download the OGG file and then play it through something like VLC, pipe that through HS sound modem, and then I've got the data. Or I could take a look at what data was actually captured from the client itself. We have both hex blobs and binary blobs here that show up as text, so that's why it's looking a little bit off. Observation-wise, I'll show this one real quick, and then all of these blue icons here are up in the up-and-coming observations in the future. So let's get rid of those and see what's just been done recently. Orange has not been vetted, so somebody hasn't taken a look at that data since it's been captured to say, yes, there's something good here, or no, there's not. Green, there is vetted data. And red, there will be not. So as you can see, we've got a lot. I mean, this has just been today. There's a lot of data there. If you're interested in that kind of data and just research-wise, research potential, it's all there. It's all open. It's all available. Anybody can go in there and make use of it. And that is my time.